Is P comma Q a point in the line y equals 2 times x plus 3? Well, in this question, finding whether a point belongs in a line whose equation we know simply means verifying whether the coordinates of such point actually satisfy the equation of the line or not. So we need to verify whether this is true or not. Q equals 2p plus 3. So two equivalent questions, and if we rearrange the terms a little bit, it would mean to verify whether 2p minus q plus 3 equals 0 or not. Let us keep this last form of the original question. Why is this convenient? Well, notice that 2p minus q plus 3, the expression of the equality in the question, appears as a factor in the two statements. So it has to mean something. Let's analyze statement 1. If statement 1 is true, then this factor on the left multiplied by the factor 3p plus q minus 5, and this product yielding 0, means that either factor can be 0. You don't know which one, though. Either 2p minus q plus 3 equals 0, or perhaps 3p plus q minus 5 equals 0, or perhaps both factors can be 0. If this possibility is verified true, this yields an affirmative answer to our question. But if this is true, okay, in this case, you can have a yes or a no for an answer. Why is that? For example, you can have two values of p and q that make this factor 0, the factor on the right, but doesn't satisfy the equation of the line above. Example, p equal to 1 and q equal to 2. You know, 3 times 1 plus 2 minus 5 equals 0, but when you insert this in the equation above, 2 equals 2 times 1 plus 3 is not true. So that means a negative answer to the question. Okay, so we are verifying that there are two possible answers. Statement 1 alone not sufficient. Well, following the same reasoning, the second statement means that there is a possibility that 3p plus q minus 7 equals 0, or 2p minus q plus 3 equals 0. The latter case would definitely give us an affirmative answer to the question. But the first case, the former case, this one here, doesn't necessarily yield an affirmative answer. Example, if p were 1 and q were 4, we know that 3 times 1 plus 4 minus 7 equals 0, right? So making this part of the OR affirmation true. But these two values, if you insert in the equation of the line, you know, 4 equals 2 times 1 plus 3, this is not true. So that means that point 1, 4 is not a point in the line. Okay? It's a no to the question, so it's not sufficient either. Same as statement 1 is not sufficient. But statements 1 and 2 taken together mean that 2p minus q plus 3 must be 0. So this means that we have an affirmative answer to the question and statements 1 and 2 are sufficient. But how is that? How can we affirm categorically that the fact that these two equations are true at the same time means that the factor 2p minus q plus 3 equals 0? Well, let's simplify this situation a little bit in the following scheme here. If you are given that x times y equals 0, and at the same time you are given that x times z equals 0, would you say from these two true equations that x must be 0? Well, not necessarily, because you might say no, y could be 0 and z could be 0. So x wouldn't necessarily be 0, could be anything. Yeah, what if to this we add the following condition? Y must be different from z. Well, if this is true, this second condition, then it follows that x must be 0. Why? Because let's say, for example, that in equation 1, you say that y is 0. But according to this second condition, z cannot be 0 because it has to be different from y. But if in the second equation z is different from 0, it follows that x must be 0. Okay? Vice versa. If you're assuming that in the second equation z equals 0, then by this condition y couldn't be 0 because it has to be different from z. But if y isn't 0 in the first equation, x must be 0. So in all cases, x must be 0 if y and z must be different. So here you can notice that in the analysis of statements 1 and 2 together, 3p plus q minus 5, this equals our statement or variable y. And 3p plus q minus 7 is like our z. And we know that these two expressions must always be different. Because if we, subtract on both sides 3p plus q, we get that negative 5 is different from negative 7 always. Yeah, two values p and q can never yield the same result for the expression 3p plus q minus 5 and 3p plus q minus 7. They will always be different no matter which values of p and q we apply. So because these two expressions, these two factors must always be different from each other, then it follows that 2p minus q plus 3 must be 0 in order to validate the two equalities. So that's why the correct answer to the question is option